It's hard to get to space. As much as we all wish there were an easy and affordable way to see our planet floating in the dark, right now, the only way is to become an astronaut or a billionaire. But there is a concept that might make it possible while serving as the starting point for the exploration of the universe, the space elevator. How exactly does it work? To understand how a space elevator will get us into space, we must first understand what an orbit is. Being in orbit basically means falling towards something but moving fast enough to miss. If you throw a ball on Earth, it makes an arc through the air and then hits the ground. In space, gravity makes you move much the same way, but if you move sideways fast enough, the curvature of the Earth makes the ground fall away beneath you as fast as gravity pulls you towards it. So to enter Earth's orbit, rockets have to go up and sideways fast. By contrast, a space elevator taps into energy from the Earth's rotation to get the cargo going fast. Imagine a child spinning a toy on a rope with an ant on the child's hand. As the ant climbs out along the rope, it starts to move faster and faster as it ascends. Compared to rockets, with cargo launched on an elevator, you only need to provide the energy to go up. Fast sideways movement comes free with the Earth's rotation. But a space elevator would, without a doubt, be the single largest and most expensive structure ever built by humans. So, is it worth it? It all comes down to costs. Rockets burn a huge amount of rocket fuel just to get a small amount of cargo into space. At current prices, it costs about $20,000 to put 1 kilogram of payload into space. That's $1.3 million for the average human, $40 million for your car, billions for an international space station. This immense cost is one of the major limitations of human spaceflight. Even with advancing technology, this cost isn't likely to be comparable with the price of an airline ticket anytime soon. A space elevator would solve this problem. After construction, a space elevator is projected to reduce the cost 100-fold to $200 per kilogram. If an inexpensive space elevator costs $20 billion, then we'll recoup our losses after launching only 1,000 tons, close to the weight of 2 international space stations. So what would a space elevator look like in real life? A space elevator has 4 major components: the tether, anchor, counterweight, and climber. The elevator part of the space elevator is the tether and the climber. It extends from the surface of the Earth to space. The climber is like a conventional elevator carriage, a chamber that works its way up and down the tether. At the base would be an anchor, pinning the tether to the Earth, along with a port for climbers. At the top is the counterweight, which holds up the tether. The tether is held tight like a rope and supported from above by the tension from the counterweight, located higher than 36,000 kilometers above the Earth's surface. At the counterweight could be a space station, a launching point for all missions from the spaceport elevator. But can we actually build one? It's hard to say. The biggest challenge is the tether. It needs to be light, affordable, and more stable than any material we can produce right now. There are promising materials like graphene and diamond nanothreads, but even they may not be strong enough. And aside from being incredibly strong, the tether would also have to withstand atmospheric corrosion, radiation, and micrometeorite and debris impacts. Additionally, it takes several days to climb the elevator. How do we power the climber? It requires a lot of energy to go up. Do we need a nuclear reactor on our elevator carriage? Or do we beam it power from the ground with a super-powered laser? And where do we get the raw materials for a 36,000-kilometer long tether? Do we make it on Earth and launch it into space, or do we make it in space and lower it down to the Earth? Could asteroid mining be the answer? Put simply, there are still some major technological hurdles to overcome. And a space elevator is not without risk. Should the tether break, it would collapse in spectacular style. If it breaks near the anchor, the force exerted by the counterweight will cause the entire elevator to rise up, ascending into space. Should it break near the counterweight, the tether will fall, wrapping around the world and whipping the end off. The resulting debris in orbit could pose serious problems to future spaceflight. If we build a space elevator on Earth, we have to do it right the first time. For these reasons, some experts have proposed first building a space elevator on the Moon. The Moon's gravity is much weaker than the Earth's, so a flimsier but existent material like Kevlar could serve as a tether. Even with all these challenges, the payoff of having a working space elevator would be immense. It might be the first step to truly becoming a spacefaring civilization. Maybe we will never build a space elevator, but in trying to do so, we might learn an awful lot. And when it comes to the exploration of the universe, there can't be too many dreams of a glorious future.